Good evening, everyone. I welcome you all to the problem solving session 8 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And today, myself, Anchor Kartiga from the Department of Chemical Engineering, IIT Hyderabad, will be handling the live session where we will be solving the problems for this week. So the class is from 6 p.m. to 8 p.m. We'll have a short 5 minutes break in between. So as far as the course layout is concerned, this is an 8-week course. So where we'll be studying all the basics of the fluidization in order to understand it completely from the start to the end. So this is an introduction part where we have seen in the previous class itself what we would be dealing in this week's class. So in week 1 to 2, we saw the introduction to the phenomenon of fluidization and the advantages and disadvantages of fluidized beds and industrial applications of fluidized beds. And in week 3, we saw characteristics of solids and we classified the solids and flow characteristics and its outline in different types of fluidization. And in week 4 to 5, we have seen the flow pattern of fluidization system and flow pattern transition, flow pattern map, frictional pressure drop and its model to analyze solid movement, mixing, segregation and staging. And in week 6, it was about gas distribution and type of gas distributors in small and large scale industries and design of distributors. Week 7, it was about bubbling fluidized bed, gas dispersion and gas interchange in the bubbling beds, mixing characteristics. And week 8, it is about entrainment and elutriation from fluidized beds. And in week 9, it is about attrition mechanisms and its analysis by model. And week 10 to 11, it is about the mass transfer phenomena, and week 12, it is about the heat transfer phenomena and the design of fluidized beds. So basically in this we haven't covered all the things. For example, solid movement, mixing and segregation and staging would be covered in the subsequent classes, and also entrainment and elucidation only introduction have been covered in this week. Further it would be covered in the next week class. So the NPTEL course covers the content behind this, wherein the professor handles all the theory behind it and all the original course content. This problem solving session is only to aid you in solving that week's assignment problem. So yeah, we'll start. And before that, the books and references for this course is that all the basics are covered in the book Cooney and Levenspil's Fluidization Engineering. And Gedaspo's multiphase flow and fluidization covers all things that we require to study the modeling aspects behind the fluidization, and Giblaro's fluidization dynamics, and S.K. Majumdar's hydrodynamics and transport processes of inverse bubbly flows. So if you people have any doubt at any point of time, please feel free to ask the question. Yeah, 1 second. We'll just add animation. So we'll start with this week's problems. So the first question is about, in a fluidized bed column, the particulate phase is an incompressible fluid with a bulk density similar to that of a fluidized bed at minimum fluidization. Select the correct option of the continuity equation of the particles. Option A, dou u x by dou x plus dou u y by dou y is equal to 0. Option B, dou square ux plus dou y by dou x plus dou square u y by dou y is equal to 0. Option C, dou square ux by dou x square plus dou square uy by dou y square is equal to 0. Or option D, none of the above. So the thing to be noted is, can anyone say this is an assumption used in a specific model, and can anyone say what is the model? I mean, which model assumes these? I mean, this statement wherein we have mentioned, in a fluidized bed column, the particulate phase is an incompressible fluid with a bulk density similar to that of a fluidized bed at minimum fluidization. Uh, Herein we have assumed the particulate phase to be an incompressible fluid where the bulk density is that of the fluidized bed at minimum fluidization condition. So this is an assumption used in one particular model dealing with the bubbling fluidized bed. So can anyone recognize which model is that? Actually, I was speaking till now and it was not shared. You people could have informed me, right? Please just let me know if there is any problems associated with sharing the screen or in mic issues. Please let me know. Like, don't be like this in future. Okay, just think of the answer. We'll discuss the answer in a minute. So the answer to this particular problem is option A, wherein it is dou u x by dou x plus dou u y by dou y is equal to 0. We all know the continuity equation is this: dou u by dou x plus dou v by dou y is equal to 0. Herein we have used dou u x by dou x plus dou u y by dou y is equal to 0. This is for particulate phase. So the particulate stream velocity is ux, smaller ux and smaller uy, which is what we have used till now. So this is an assumption from the Davidson model 1961, wherein the particulate phase is assumed as an incompressible fluid with a bulk density similar to that of a fluidized bed at minimum fluidization condition. So if that assumption is made, the continuity equation is given as this, and then with these and together with the further assumptions, the model equation is framed. What is the second assumption? Second assumption is nothing but the relative velocity between the pressure and the fluid is proportional to pressure gradient. That is, the relative velocity is nothing but the difference in velocity between the fluid and the particle. That is proportional to the pressure gradient. And the third is nothing but the fluidizing fluid is also assumed to behave as an incompressible fluid with a constant voidage at minimum fluidization condition. So we have one more continuity equation with the velocity of the fluid. And with these three equations, if we substitute it in the pressure gradient equation, we get a equation for the pressure distribution, wherein we can the equation obtained is of the form dou square p by dou x square plus dou square p by dou y square is equal to 0. It is the equation for the fixed bed. So we can say that the pressure distribution in a fluidized bed is unaffected by the motions of the particles in the fluidized bed. So since it is similar, so we can say the pressure distribution in a fluidized bed is unaffected when even with the motion of the particles. What is the fourth assumption in the Davidson model? The pressure throughout the bubble is constant, and the particulate phase behaves as an inviscid liquid, and also the bubble is assumed to have a circular cross section. So with all these model assumptions, the equation is framed, and the first equation is dou ux by dou x plus dou uy by dou y is equal to 0 for the particulate phase. So it is a continuity equation of the particles. We will see question 2. In question 2 it is asked which of the following is correct for slow bubble regime. UB is equal to UMF into epsilon MF. UB is less than UMF into epsilon MF. And UB is greater than UMF into epsilon MF. UB is less than UMF by epsilon MF. So please find out the answer and we'll discuss the answer in a minute. You people can also unmute yourself and answer the question. Together with the answer, try to give a proper explanation, or else just think of the answer with the proper explanation. So the right answer is the bubble velocity should be less than UMF by epsilon MF. Option D is the right answer, wherein bubble velocity is less than UMF by epsilon MF. So what does slow bubble mean and what does fast bubble mean? Slow bubble means that if this is the bubble, the gas enters from this way and it moves towards the top. Fluid moves up relative to bubble. That is, the fluid moves up relative to the bubble, and there would be this region where the fluid penetration does not takes place. So in this region, in slow bubble regime, fluid moves up relative to bubble. So where does this takes place? When we are using larger particles or when small bubbles are getting formed, the slow bubble regime is observed. Slow bubble regime is observed when we are using large particles or small bubbles are getting formed. Small bubbles are getting formed. So this is known as slow bubble regime where UB is less than UMF by epsilon MF. We'll move to question 3. In question 3 it is asked that choose the correct option for the fast bubble regime. UB is greater than UMF by epsilon MF. UB is less than UMF by epsilon MF. UB is equal to UMF by epsilon MF. None of the above. So we have seen what the answer is for slow bubble regime. So now think of what would be for the slow fast bubble regime and what would be the option. What would be the reason? So in fast bubbles, fluid moved down relative to the bubbles. Whereas in slow bubbles, it was observed that the fluid move up relative to bubbles. In fast bubbles, the fluid is moving down relative to bubbles. The gas streamlines would be like this in the fast bubble regime. So as you can see, this would be involving the cloud. So gas streamline is this. So in this option A is the right answer because as we all know that UB less than UMF by epsilon MF leads to slow bubble regime. So for the fast bubble regime it is the exact opposite. UB must be greater than UMF by epsilon MF. So answer is option A where UB is greater than UMF by epsilon MF is the right answer. So In this actually, the cloud region for the bubbles would be till this. This would be from here to there, it would be r, that is the radius of the cloud, and this inside region would be the bubble, that is rb. We'll go to question 4. In a fluidized bed column, the relative velocity between the gas and the particle in the x direction can be represented as, this one we discussed just few minutes back. So can anyone answer what does this statement mean and what the statement, I mean where the statement is from? Like this one is from related to question 1, as I can say. So can anyone remember what model we talked about in question 1? Okay, it is Davidson model 1961. So in it is an assumption, second assumption in the Davidson model, wherein the relative velocity between the gas and the particle is proportional to the pressure gradient. So how do we represent this? Ug minus us at x direction is equal to minus k by 2 dou p by dou x, or ug minus us x is equal to minus k dou p by dou x, or ug minus us at x is equal to minus k square dou p by dou x, or none of the above. So we all know that it is proportional to the pressure gradient. So the relative velocity is gas velocity minus solid velocity. Ug is nothing but gas velocity and us is nothing but solid velocity in this. So it is proportional to the pressure gradient. This is the assumption we saw in the what is it? Davidson model 1961. So from this we can say that since it is at x, we are using x. So here it is ugx, so and usx my is equal to minus proportional to dou p by dou x. So it is equal to minus k dou p by dou x. So answer is option B. Ug minus us at x is equal to minus k dou p by dou x is the right answer. It is proportional to the proportional to the pressure gradient, and the proportionality is given by k. It is not k square or it is not k by 2, it is proportional to k. In other words, we can also write it as ug at x is equal to us at x minus k times dou p by dou x. It is the same equation wherein we have used it in the left hand side, like we have taken it to the other side and used. So this is question 4, wherein we have seen the relative velocity between the gas and the particle in the x direction can be represented as ug minus ux is equal to minus k dou p by dou x. I hope this is clear. We'll go to question 5. If you have any doubts, please feel free to ask at any time. Also, participate in the discussion actively by answering the questions when I ask, so that it can be cleared as and when you can go. In question 5, it is asked that we have gone to question 5. In question 5, it is asked that in the fluidized bed column, typical bubbles are not spherical. The region below the bubble is the wake region. The wake fraction below the gas bubble is defined as Fw is equal to Vw square by Vb, Vb by Vw, Vw by Vb, or Vw by Vb square. So can anyone give the answer? If you are not willing to answer, just take a pen and paper and put it put the answer so that you can verify it once we discuss it here, so that it will be easy for you people as well uh, to cross check it. Because once you think of an answer and mark it right, you would have some solution behind it and the methodology behind it. So once I discuss it as well, we can just verify it so that you can have newer doubts as well, so that would lead to more creative answers. So just think of it and we'll do. So as in this as well, just think what would be the answer behind it. So it is mentioned that in a fluidized column, typical bubbles are not spherical. So, what we were speaking, typical bubbles are not spherical. Although in Davidson model, we assume the bubbles to be spherical, the typical bubbles are not spherical. Rather, they would have wake, sorry, it would be like somewhat like this, where here the wake of solids would be there. Wake of solids would be there, and so this wake fraction, this is the wake fraction, together when put we can observe it to be somewhat spherical. So what, this is wake, and what is the wake fraction given the gas bubble volume is the VB. So if we assume the volume of the bubble as VB and volume of wake fraction as VW, what is the wake fraction? In this itself we can assume, right? This is one whole thing and this is one small portion of wake. So this remaining portion is bubble. I mean together with everything would be bubble. So wake fraction is defined as Fw is equal to Vw, that is volume of wake, divided by volume of bubble. Vb is the right answer. This Vw by Vb is the right answer. Fw is equal to Vw by Vb, because this is the volume of bubble and this one is the volume of wake. Volume of wake is calculated using the theta W. It is the angle of wake or the wake angle. This is from the model of Rowe and Partridge, 1965. Rowe and Partridge 1965 model. So where they defined that typical bubbles are not spherical, rather they have some wake left behind them. So with those wake, the bubble forms spherical shape. So what is the volume fraction of, sorry, wake fraction? It is the volume of wake by the volume of bubble is given by VW by VB. FW. So answer is option C. FW is equal to VW by VV. I hope this is clear. We'll go to question 6. In question 6, it is asked that in a bubbling fluidized bed reactor of diameter 0.40 meter, the sorted mean bubble size is measured to be 4 mm. Calculate the bubble rise velocity in mm per second. G is equal to 9.81 meter per second square. Where UBR is option A, it is 135.58 meter per mm per second, or option B, it is 125.98 mm per second, option C, it is 200.25 mm per second, or option D, it is 140.84 mm per second. So we'll calculate this. If you people want, just take a minute and write the answer, or try solving it. We'll solve it in a minute. So we'll solve this. First, we'll write all those given. What is the diameter? Bed reactor of diameter. Okay. D bed diameter of bed is 0.4 meter. Water mean bubble size is measured to be 4 mm. Bubble diameter 4 mm. D bubble 4 mm. Bubble rise velocity to find bubble rise velocity in m per second. G is equal to 9.81 meter per second. So we need to find bubble rise velocity, BR. So can anyone give the formula to be used in this particular question? First we need to check what is dB by d bed. By d bed, it is nothing but what is okay, sorry, not this. 4, okay, dB, it is dB by d bed, 4 by 0.4. Okay, so it is, what is this, 400 mm, 4 by 400. 4 by 400 is equal to 0.01. Since this is less than 0.125, we can use this formula. UBR is equal to 0.711. Okay, insert UBR is equal to 0.711. So this is the formula. So UBR then is equal to UBR is equal to 0.711 into G is dB is 4 into 981 centimeter. One more, 10 power minus 1 by 10 power minus 1 power 0.5. So what is it? Is equal to 0.711 into it is equal to 198.494 into 0.711. 0.711. This is equal to 141.13 mm. Yeah, almost the right answer. We have got 141 and it is 140. If it is 140.93, it is 0.71. 140.93 mm. So the bubble rise velocity is therefore 140.93 mm per second. 140.84 mm per second. Option D is the right answer, where we have got 140.93 mm per second. So, hmm, we'll go to question 7. I hope this one is clear. This you people have understood clearly. Now we'll go to question 7. In question 7, it is asked that a fluidized bed reactor of diameter 45 centimeter working for coal gasification with minimum fluidization velocity of 0.025 meter. It should be meter per second, I guess. The average size of the coal particles was found to be 272.0 micrometer, for which the minimum voidage is about 0.55. The measured sorter mean bubble size is approximately 10 mm. For this fluidized bed, calculate the cloud radius in mm. Use G is equal to 9.81 meter per second square. So it is given that bed diameter is 45 centimeter working for coal classification with minimum fluidization velocity of 0.025 meter per second. The average size of coal particles was 272.0 micrometer, for which the minimum voidage is 0.55. So it is the mean bubble size is given as 10 mm and the measured sorter mean bubble size is given as this. For this fluidized bed reactor, calculate the cloud radius in mm. G is equal to 9.81 meter per second square is given. So we'll see how to solve this. As before, take your time and solve this. We'll solve it after 2 minutes. Since it is a bigger question, just take 2 minutes of time and we'll solve this. So we'll solve this problem. For that we'll, as always, we'll write the given first and then we'll proceed. This is question sum. Actually, only 2 problems are given for this week. All the rest are from theory questions only. So just take your interest and solve this. First, we'll write the given, or we'll keep the given here. Given bed diameter is given, dBE. Bed diameter 45 centimeter. Working fluid with the minimum fluidization velocity U MF, minimum fluidization velocity 0.025 meter per second. Average size of cold particles, particle diameter dP particle diameter voidage is about 0.55. So what is minimum voidage? How do we denote it? We denote it using epsilon mf. mf minimum voidage 0.55. Sorter mean bubble size is 10 mm. Bubble diameter dB bubble 10 mm. For this fluidized bed, calculate cloud radius in mm. Find cloud radius in mm. So these are all the given. We need to find cloud radius. So can anyone mention what formula we should use for this particular problem? No one with the answer. It's okay. We ourselves will solve. No issues in that. So first step is to calculate UMF by epsilon MF. Do we have UMF? UMF is there. Epsilon MF is also there. 0.025 by 0.55. UMF by by MF is equal to what is it? 0.25 by 0.55. 0.025 by 0.55. 0.025 divided by 0.55, which is equal to 0.025 divided by 0.025 0.55. It is 0.045. 0.04545. Now, okay. Similar to the previous problem, you need to find the bubble rise velocity. Before finding the bubble rise velocity, yeah, before finding that, we need to find what is d bed by db by d bed. db by d bed. What is db? 10 mm. D bed is 45 centimeter. dB is 10 divided by 450. What is it? 1 by 45. 0.02222. Again, this is less than 0.125. So we can use UBR is equal to 0.71171 into GdB power 0.5. 0.71 into 9 point, okay, 98010 into 10 power 0.5. 9810 into 10 0.71 into 313.2091. 0.71 into answer 222.38 mm per second. Meter per second. Or this is 45 mm per second. We all know that if UBR is greater than UMF by epsilon F, then it is fast bubble. For fast bubble, R by RB is equal to UB divided by UMF by epsilon MF plus 2 divided by UB divided by this minus 1, and we will keep it power here. So how do we substitute it? This one is equal to, this is 222.38 divided by 45 plus 2 divided by 222.38 divided by 45 minus 1. What is this? 38 divided by 45 is actually 4.9417 plus 2 divided by minus 1. So this one is equal to plus answer plus 2 divided by 1.7610. So what would be R by RB is equal to, we'll continue it in the next page. Question 7, solution continued. One 1.2076. So R is equal to 1.2076 into 10 by 2, that is 5, into 5 is equal to 6.0380 mm. This is radius of cloud. Diameter of cloud is equal to 12.76 076 mm. So we'll see what the options were given. 6.05 mm or we have got 6.08 mm. So both of them are right answer. So this is how we do this problem. Radius of cloud RC is equal to 6.04 mm. So we'll just quickly go through how we did the problem. First we have written all the given things from the problem statement, and then we have found UMF by epsilon MF and compared it with the UBR. If UBR, or else we can give it as UB. We have found UB, bubble rise velocity. For finding bubble rise velocity, we have found out if dB by dB bed is less than 0.125 or not. Since it is less than 0.125, we have used the UB formula as this 0.71. From this formula, we have found out UB. Since UB is greater than UMF by epsilon MF, we have found it to be as fast bubble. So for the fast bubble, RC by RB cube is given by using this formula. So we have substituted all the known terms in this given formula, and for the further we have found RC by RB as this. So we know the RB as 5 mm. So substituting 5 mm in the final step gives RC, that is radius of cloud, as 6.04 mm. So this is the procedure. If you have any doubt, please ask, or we will move to next question. Okay, let us just take a 5 minutes break. After that, if you people have any doubts in this question, we will discuss that and then move on to the next question. So we'll resume the session now. I hope there is no doubts in this. We'll move on to next question. In question, yeah. In question 8, it is asked that choose the correct option regarding the slugging fluidization. Wall effect negligible if dB is less than 0.1 of the bed diameter. Wall effect negligible if dB is greater than 0.1 of the bed diameter. Wall effect negligible if dB is equal to zero point 0.1 of the bed diameter. Wall effect negligible if dBE is less than 0.105 of the bed diameter. So here dBE is nothing but equivalent bubble diameter. In general, there are three types of flux that is formed inside a fluidized bed. The first one is round nose slugs. Here, uh, it is round shaped and it is frequently observed in gel at A or gel at B. All these you would have listened when you have seen the lecture videos. This is just for a quick recap. And next is the wall slugs, wherein small bubbles grow and they attach with the walls. This is observed in case of large particles and they move faster than the round nose slugs. And the last one is flat slugs where they almost occupy the size of the vessel. This is observed in case of cohesive particles like gel at C and or angular particles. So solids rain down in order to move inside the fluidized bed. So when does wall effect become significant? When dB is greater than 1 by 3 of the bed diameter. Or in other words, if it becomes negligible when bubble equivalent diameter is less than 0.1 times of the bed diameter. So answer is option A. Wall effect becomes negligible if bed bubble equivalent diameter is less than 0.1 times of the bed diameter. So this is round nose. Since it is nose is like round, this is wall slug and this is flat. So I hope this is clear. We'll go to question 9. In question 9, it is asked that which of the following statement is correct. If dBE by d bed is less than 0.6, it is slugging bed. If dBE by d bed is greater than 0.6, it is bubbling bed. If dBE by d bed is less than greater than 0.6, it is slugging bed. If dBE by d bed is equal to 0.6, it is slugging bed. So in this itself, we can observe one thing. So either this one can be true or this one can be true. So what do you think? If dBE by d bed is greater than 0.6, it is slugging bed. It is not bubbling bed, it is slugging bed. So the answer is option C, dBE by dBed. That is bubble equivalent diameter by bed diameter is greater than 0.6, it is known as slugging bed. If it is less than 0.1, it is wall effect becomes negligible. If uh, it is greater than 0.6 or 0.67, wall effect becomes significant and it is known as slugging bed. So if dBE, that is bubble equivalent bubble diameter by bed diameter is greater than 0.6, it is known as slugging bed. Answer is option C, that is if dBE by dBed is greater than 0.6, it is slugging bed. As you can see from the options, you can easily ignore one of the options and go for the other. In this case, B and C, either only one of the statements could be true, right? Because if it is greater than 0.6, it can either be slugging bed or it can be bubbling bed or it can be none of the above, I mean none of them. But in this case, it is all three options are given, greater than or equal to or less than. So answer is greater than 0.6, so it is known as slugging bed. You can easily ignore the option B actually in this case. So answer is option C. We'll go to question 10. In question 10, it is mentioned that select the correct expression for the bed expansion of a bubbly fluidized bed. L by LMF is equal to 1 by epsilon, 1 minus epsilon by 1 minus epsilon MF. L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon. Or L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon. Or it is none of the above. So we all know that in the bubbling bed, L by LMF is equal to 1 minus epsilon MF divided by 1 minus epsilon. So it is L divided by LMF. So you can see that L into 1 minus epsilon is equal to LMF into 1 minus epsilon MF. That's what we see, right? So it is, since they are equal, it is given as a ratio aspect. L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon is the right answer. Okay. Actually, both option A, B and C are the same actually. I am not able to find any difference in this. So, I mean, both are same. L by LMF is equal to 1 minus, maybe we can remove one of them, that is option B. L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon. Option B is the right answer. This is in case of bubbling fluidized bed. So the correct expansion for the bed expansion of the bubbling fluidized bed is equal to L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon is the right answer. So option B is the correct one. We'll go to question 11. In question 11, it is given that the wall slugs move faster than the round nose slugs and its motion can be defined as U wall slug is equal to 0.35 into 2 times of G d bed power 0.7, or U wall slug is equal to 0.7 times G times d bed, or U wall slug is equal to 4 by 3 into 2 times of G d bed power 0.5, or d bed is equal to 0.35 times 2 square root of 2G d bed. So actually, we have seen that what is, do you people remember what is round nose slugs? It is looking like this, and wall slugs are where they would be attached to the walls. So all we have seen that wall slugs move faster than the round nose slugs. So what is the answer? Answer is actually option D, 0.35 times 2 square root of 2 times GD bed. So this is observed in case of larger particles like delta T. The slugs would be moving in association with the wall. Wall effects would be very predominant. So therefore it is known as wall slugs. So answer is option D. U wall slug is equal to 0.35 times 2 square root of 2 times of GD bed. I hope the answer is clear. We'll go to question 12. In question 12, it is given that for the slugging fluidization, choose the correct option. Option A, wall effect predominates if dBE is less than 1 by 3 of the bed diameter. Option B, wall effect predominates if dBE is greater than 1 by 3 of the bed diameter. Or option C, wall effect is negligible if dBE, that is a bubble equivalent bubble diameter, is greater than 1 by 3 of the bed diameter. Or option D, wall effect predominates if dBE is greater than 1 by 3 of the particle diameter. So on seeing this itself, we can ignore one option. What is that option? Can anyone say? Well, it is option D. On seeing that itself, we can ignore because we are not relating particle diameter with the bubble equivalent bubble diameter. So from we have to choose from option A to C. Uh, Wall effect predominates when the bubble size is larger compared to the bed diameter. That is, it is almost occupying some space of the bed. Then the wall effect predominates. So in that case, option A, it is given by dBE is less than 1 by 3 of the bed diameter. So if it is less than the bed diameter, 1 by 3 of the bed diameter, it is not playing a very major role, right? We cannot uh, say that wall effect is predominating in that case. We can say it is negligible. Option B, it is given that wall effect predominates if dBE is greater than 1 by 3 of the bed diameter. So this is the right answer, where we can say that if the bubble size is almost the size of the bed, then we can say that wall effect is predominating. Option C, it is given wall effect is negligible if dBE is greater than 1 by 3 of the bed diameter. It is not negligible, it is predominating in that case. So answer to this particular question is option B. Wall effect predominates if dBE is greater than 1 by 3 of the bed diameter. Think again. We'll discuss if you people have any doubts, or else we'll continue with the next question. So yeah, actually this is an image representing this. Initial bubble formations, they are very small. With freely bubbling bed, they grow in size, and they grow in size, as you can see, they are occupying some space across the bed. And here the wall effect is predominating, so wall slugging takes place where the walls influence the bubble formation and bubble size. And this is axisymmetric slugging, where we can see if it is equal in this and that side. So this is taken from this paper, experiment support simulation by the Neptune CFD code in an upflow bubbling fluidized bed reactor, from Chemical Engineering Journal. So if you want, you can read this paper. This is just an image reference to let you know how bubble formation turns into slug formation across the fluidized bed, bubbling bed. So we'll go to question 13. In question 13, it is asked that according to Stewart and Davidson 1967 model, slug terminal velocity can be defined as slugs in the fluidized bed, UBR is equal to 0.361 GdBE power 0.5, or UBR is equal to 0.5 GdBE 0.5. Slugs in the liquid solid slurry, bubble rise velocity is equal to 0.35 GdBE power 0.5, or P UBR is equal to 0.35 GdBE, that is equivalent bubble diameter 0.5. So we need to match it for the slugs in the fluidized bed and the slugs in the liquid solid slurry. So can anyone match? We will see the option. First, it is 1 and R. Sure. PQRS. So actually, in this we know one answer. We know the slugging fluidized bed uh, diameter. So actually, for slugging fluidized bed, we have seen it as 0.35 GdBE power 0.5. That is, this is for the bubble rise velocity in the slugging fluidized bed. So for slugs in the fluidized bed is UBR is equal to 0.35 square root of GdBE. 1 R is the right answer. So 1 R. So B and C are wrong. So 2P or 2S. Slugs in the liquid solid slurry. What is P? P is 0.361 into GdBE power 0.5, or 0.35 GdBE power 0.25. So it doesn't vary that much. So the right answer is 0.361 GdBE power square root. Sorry. Liquid solid slurry, it is 0.361 GdBE power 0.5, and slugs in the fluidized bed, it is 0.35 GdBE power 0.5. That is, both are square root only, not any other roots. So for UBR is square root of GdBE into some constant value. That constant is 0.35 for the liquid solid fluidized bed, and for the liquid solid slurry it is 0.361. So 1R and 2P is the right answer. So answer is option A, 1R 2P. We'll go to question 14. According to Kehoe and Davidson model, 1973 model, select the correct option regarding the slug frequency. Slug frequency is independent of operating velocity. Slug frequency is independent of operating velocity. That is option A. Option B, slug frequency is dependent on operating velocity. Option C, it is slug frequency is 1 by 3 times of the operating velocity. Or option D, it is none of the above. According to Kehoe and Davidson model, slug frequency is given by U minus UMF divided by LS. LS is nothing but the length of the slug. Or in other words, this can be given as this. U minus UMF is given by 0.35 square root of G times NT. NT is nothing but it is the defined as the number of bed diameters between the rear of the leading bubble and the trail of the nose of the trailing one. So if two bubbles are this, so between these two, how many bed diameters can be fitted is given by NT. So NT into square root of D diameter of the bed. So this is the final formula. So it does not depend on the operating velocity. So slug frequency is independent of the operating velocity is the right answer. Option A is the right answer. Option A, slug frequency is independent of the operating velocity. According to Kehoe and Davidson model, slug frequency is independent of the operating velocity. So just I hope you understood. If you have any doubt, ask, or else we'll move to question 15. That is the last question for this session. We'll go to question 15. In question 15, it is asked that the minimum height in the bed at which complete slugging sets in according to Bayes and Geldat 1974 model is, the minimum height in the bed at which complete slugging sets in is HMFS is equal to 0.6 times D bed power 0.175, where D bed is in centimeter, or HMFS, that is minimum fluidization height, is equal to 60 times of diameter of the bed to the power of 0.175, where D bed is again in centimeter, or HMFS is equal to 6 times of D bed power 0.175, D bed is in centimeter, none of the above. So what does this question means is that according to Bayes and Geldat model, the minimum bed height should be something above which complete slugging sets in. So if the bed height is less than this, that is in shallow beds, slugging would not occur. So what is this height? How do we calculate it? It is given by this formula, where it is raised to the power of D bed is raised to the power of 0.175. The right answer is 660 or zero point 0.6. Mm, so answer is actually 60. Mm, mm, they actually in their paper they found out the effect of particle size or size distribution on slugging and found out it was not affecting the particle size or particle size distribution was not influencing the slugging behavior, but uh, the bed height should be more than this. That is, if uh, the bed height, if it is more than HMFS, slugging was found to occur. If it is less than this, in shallow beds, slugging was not occurring. So answer is option B. As we said, it is 60. 60 D bed 0.175. Bayes and Geldat minimum slugging effect of bed diameter and height, particle size and size distribution was studied for beds deeper than the critical bed height. So yeah, this is what we have seen also. So if you people have any doubt, we'll discuss it, or we'll have a quick recap of the concepts we saw in this class and close the session. If you have no doubts, you can leave the session also. I thank everyone for attending today's session. Tomorrow, I mean not tomorrow, next Friday, we'll again meet at the same time. And thank you. Like, we'll meet at the same time and discuss next week's problems. It would be mostly focusing on elutriation and entrainment, which is nothing but the carryover of solids from the bed. So yeah, if you have any doubts, please ask, or else we'll have a quick recap and close the session. So actually, these are all the problems. In this week, we have seen about the bubbling fluidized beds, and it was mostly about, initially we saw about the Davidson 1961 model with the following, assumptions like the particulate phase was assumed to be an incompressible fluid with the bulk density similar to that of the fluidized bed at minimum fluidization condition, and one continuity equation was obtained from that. And the second assumption was that relative velocity between the fluid and the solid phase is proportional to the pressure gradient, and also the fluidizing fluid is assumed to be incompressible at with constant voidage epsilon mf. And the fourth one was pressure throughout the bubble is constant and the particulate phase behaves as an inviscid liquid. And the bubble was assumed to have circular cross section in Davidson model, even though it might not be the case everywhere. And we have seen about two bubbling regimes, slow bubble regime and fast bubble regime. In slow bubble regime, the fluid moves up relative to the bubble, whereas in fast bubble regime, fluid moves down relative to the bubble. Slow bubble regime was observed when UB is less than UMF by epsilon MF, whereas in the reverse case, UB is greater than UMF by epsilon MF. Fast bubble was observed. In fast bubble, internal circulation was observed for the fluid. Uh, Slow bubble regime was observed for case with larger particles and smaller bubbles. And in stationary bubbles, there are various transitions from slow bubbles to faster bubbles. Um, and then it was also pressure distribution across the bubble is also important, whereas the gas enters from the lower region and comes out from the higher region, sorry, a top portion, because in the lower portion the pressure is less than the surrounding fluidized bed, whereas in the up portion it is the reverse case, the pressure is higher than the surrounding fluidized bed. Bubbles are not concave, bubbles are not spherical also, they can be concave, flattish at the bottom, because they have wake which carry some solids. So this wake portion is modeled according to Rowe and Partridge, where in according to them theta w is the wake angle and Vw is the volume of the wake. So volume wake fraction is given by Vw by Vb, and if for that we have seen various values. And then the focus was shifted to slugging beds. In slugging beds it is not preferred because they deteriorate the mixing quality inside the fluidized bed. And we have seen three types of slugging. One is round nose slugging, and next is the wall slugging, and then third is the flat nose slugging. In round nose slugging, it is commonly observed in gel at A or B particles. In wall slugging, it is observed with the case of larger particles like gel at D, whereas flat nose slugging is observed in case of coercive particles. And we have seen various conditions, like if a diameter of the bed, sorry, bubble equivalent diameter is greater than 1 by 3 of the diameter of the bed, wall effect is predominating. Wall effect is negligible if the bubble equivalent diameter is less than 0.1 times the diameter of the bed. And Stewart and Davidson in 1967 found out a slugging criteria for the fluidizing velocity, and also from that it was various correlations were found out for the bubble rise velocity or the fluid velocity inside the bed. And Kehoe and Davidson model proved that slugging frequency is independent of the operational velocity. Bayes and Geldart also found out a minimum height required for slugging. If the bed height is less than that, slugging was not found to occur. Similarly, correlations for free bubbling regime, the height of the free bubbling regime is also found out from their correlations. And finally, it was also observed that L by LMF is equal to 1 minus epsilon MF by 1 minus epsilon in case of bubbling bed. So we have seen few problems in yeah, the next one is the problem how to find out the bubble rise velocity. The first is we have written given, and next we found out dB by diameter of the bubble by diameter of the bed, and if it is less than 0.125 the bubble rise velocity is given by this formula. So So on substituting that, we can get the bubble rise velocity. This is a very straightforward problem. And the next one is the found radius of cloud we need to find. So to find that, first we found out UMF by epsilon MF, since it is greater than, and then we found out UB. Since UB is greater than UMF by epsilon MF, this falls under the category of fast bubbles. So for fast bubbles, for finding out UB, again we found use the method similar to the last problem. And for fast bubbles, the cloud diameter is given by this formula, and on substituting everything in this, we are obtaining the result. So everything is a simple correlation formula, I mean simple formulae, where depending on the criteria, certain criteria we are using it in certain situations. Only those. So it is a straightforward problem, so there is no worries. Yeah. Yeah, these are all the problems for this week, and it was mostly about all other things I think we have observed, right? Yeah, thank you. I thank everyone for attending this week. We'll meet again next week. If you have any doubts, you can ask, or else we'll close the session.